Hi guys, I'm Monica. Welcome back to my channel Aerocar. So in our journey of aerodynamics, we proceed with the elementary flows. So elementary flows are nothing but the building blocks for analyzing complex flows, and especially when the flow is incompressible, irrotational. For such kind of flows, we use these elementary flows, and our first elementary flow that we are going to discuss would be uniform flow. Now, what is a uniform flow? When I say the word uniform, there is a certain picture that comes into your mind, right? Like maybe the flow might be something like this, or maybe like this, which is moving uniformly without any kind of disturbances, right? So a uniform flow, if you want to define it in technical terms, a uniform flow is a physically possible, incompressible flow and an irrotational flow. Now, when I say incompressible flow, the mathematical condition that an incompressible flow satisfies is this. And when I say irrotational flow, the curl of the velocity becomes 0. So if I want to write velocity potential for the uniform flow, then how can I write? Can I write velocity potential as something of this sort for a uniform flow? Correct? So this would be my velocity potential for uniform flow. Now what we are going to do is we are going to consider a uniform flow in a flow field and observe it closely and derive or obtain equations from that uniform flow. So now let us consider a uniform flow in a flow field which is moving in x direction. That is, the flow direction is in x direction of the coordinate system. And this uniform flow has a free stream velocity v infinity. So as discussed a few minutes ago, a uniform flow is a physically possible, incompressible and irrotational flow. Now we had derived some equations for the velocity, that is writing velocity in all the three directions in terms of phi. So that is u is equal to dou phi by dou x, and then you have v is equal to dou phi by dou y, and w is equal to dou phi by dou z. Correct? Now if you refer to this diagram, and the arrows would be pointing in this direction, the flow. If you look at the diagram, and if we take these velocities as our reference, so I can write dou phi by dou x, which is equal to u is equal to v infinity. Correct? Because this is my x direction velocity over here, right? And what would be my velocity in y direction? That is dou phi by dou y, which is equal to v. It would be equal to 0. Correct? So let us say this is our 1a and this would be our 1b. So now what we will do is we will integrate this equation 1a with respect to x. Integrating 1a with respect to x. So upon integration, I get phi is equal to v infinity x plus f of y. Say this is my equation 2. Now this term fy is a function of y only. Similarly, what we will do is integrating 1b with respect to y. So upon integration, I get phi is equal to constant plus g of x. And here g of x would be a function of x only. So now we see that in these two equations, that is equation 2 and 3, phi is the same function, correct? So if I compare both these equations, that is equation 2 and 3, so g of x would be v infinity x, correct? because it is a function of x, I can write g of x as v infinity x and f of y as constant. So which means I can write phi as v infinity x plus constant upon comparing these two equations. Now, after deriving this equation, there is some important point that we have to discuss about. If it is a practical aerodynamic problem, the actual value of phi is not significant. Rather, phi is always obtained by the differentiation of velocity. So that is, I will obtain, by the differentiation of phi, we will obtain the velocity. So this is how I will obtain velocity. Now if I apply this derivative principle to this equation 4, the derivative of a constant would be 0, correct? Which means I can write phi is equal to v infinity x. This would be my equation 5. Now this equation 5, the velocity potential for a uniform flow. So this is the velocity potential for a uniform flow with velocity v infinity, which is oriented in the positive x direction. Now, one more thing to be noted about this velocity potential, which is given by equation 5, is that it does not depend on the assumption of incompressibility. We have not assumed anywhere over here that my flow is incompressible. It is irrespective of that. So, it applies to any uniform flow, either compressible or incompressible. Here, as I said, that is in practical aerodynamic problems, the actual value of phi is not significant. Phi is always used to obtain the velocity by differentiation. Alright, now let us consider the incompressible stream function, that is psi. Now we know we can write velocities in terms of psi as something of this sort, where u is equal to dou psi by dou y and v is equal to minus dou psi by dou x. Correct? So if we look at the figure and if we are writing dou psi by dou y, how can I write dou psi by dou y, which is equal to u, would be equal to v infinity, whereas dou psi by dou x, which is equal to minus v, would be equal to 0. Let us say this is our equation 6a and this would be our equation 6b. So now what am I going to do is integrate equation 6a with respect to y and 6b with respect to x, the similar procedure that you had followed, and then comparing the results, we would get the final equation for psi as v infinity y. The same thing that we did here for velocity potential, the same thing for stream function. So this would be our equation 7. This equation 7 is the stream function for an incompressible uniform flow which is oriented in positive x direction. Now one thing we know that if I say psi is equal to constant, this would be my equation of streamline, correct? So which means if it is equation of streamline, I can write it as psi is equal to v infinity y is equal to constant. Yes, the streamline for uniform flow can be given by this equation. If I want to write the equation of streamline for an uniform flow. Now, because v infinity is itself constant, the streamlines can be mathematically written as y is equal to constant. They can be mathematically denoted in this way. Y is equal to constant. So which means when I say y is equal to constant, if you look at this figure, the horizontal lines are showing me y is equal to constant, correct? And if I say x is equal to constant, that will be represented by this dashed line. This dashed line represents x is equal to constant. So when I say y is equal to constant, which means psi is equal to constant. that is this horizontal line. And when I say x is equal to constant, my phi will be equal to constant, which is this vertical dashed line. So when we say psi is equal to constant and phi is equal to constant, and if you look at this figure carefully, these two lines are mutually perpendicular. And if you can recollect that there was some particular name we had given for this phi is equal to constant. So these are called as equipotential lines, correct? And psi is equal to constant as is our streamline. So in our previous video where we were discussing that equipotential lines and streamlines are perpendicular, so the same thing we are observing over here, that is equipotential lines and streamlines are mutually perpendicular. Now if I want to express this equation 5 and equation 7 in terms of polar coordinates, that is x can be written as r cos theta and y can be written as r sin theta. So what did you have? Phi is equal to v infinity r cos theta and psi would be equal to v infinity r sin theta. So this is in terms of polar coordinates. Let us say this is our equation 8 and this would be our equation 9. Now let us introduce the concept of circulation in this uniform flow. Now you might have a question, how come we have circulation in a uniform flow? Let us see how does this come into picture. So if you want to define circulation or maybe write circulation mathematically for that matter, so it would be a cyclic integral of VdS, correct? This would be the mathematical representation. Let us name this as A. Now what we are going to do is we are going to consider this enclosed curve, this dashed curve, as you are able to see in the figure, in the uniform flow. So H and L are the lengths of vertical and horizontal sides respectively of this rectangle. Based on these horizontal and vertical lengths of this rectangle, if I'm supposed to write the equation of circulation, let us see how we can write it. So upon substitution, this is what we get, that is circulation is equal to 0. Now this equation 10, it is true for any arbitrary closed curve you are considering in an uniform flow. Now in order to show this, let us say V infinity is constant, okay, in magnitude and direction. So if I say my V infinity is constant, what will I write circulation as? V infinity comes outside over here. Now why this has gone to 0? Because the line integral of ds around a closed curve is identically 0. That is why we get it as 0. So therefore from equation 10, what can we state? That the circulation around any closed curve in a uniform flow is 0. So this result, whatever we have obtained, is consistent with the Stokes theorem, right? Which we had used earlier, the Stokes theorem. Now, one more thing we know, that is a uniform flow is irrotational. And when I say my flow is irrotational, the curl of my velocity is 0 everywhere, correct? So if using the Stokes theorem, if I write circulation in this form, in terms of Stokes theorem, my curl of velocity is 0, which in turn tells me that my circulation is 0. So this was all about the first type of elementary flow. In our further discussions, we will be proceeding with the other types of elementary flows as well, and some interesting facts about elementary flows, and also some realistic examples also we will discuss. So thank you for listening. Stay tuned.